Hey folks, this is Major Jones here to give you our first lesson on FSMs, which is short for finite state machines. This is a really powerful category of devices that's going to help us solve a whole bunch of problems. And so my goal today is to help you kind of understand conceptually what these devices are. So to begin with, I'll draw your attention up here to say, I've got two examples of circuits we might want to build out of digital logic. In one of them, we are trying to count the number of ones in an 8-bit binary number. So for example, if the input is 0100 1001, the output would be 3, since there are 3 ones in that number. And that should be pretty clearly, like you can design, a digital logic circuit to do that. It might take a while because you've got 8 inputs, right? But it's very clearly a one-to-one mapping of one input to an output. Even if I kind of make it slightly more complicated, it's still pretty clearly combinational logic. Let's say I want to design the same circuit, but I'm going to have a little switch that controls whether or not the circuit sort of counts the number of ones in the number or counts the number of zeros. Maybe that's useful, right? So using the same number as above, if in this circuit, if I were to flip the switch, the output instead of being 3 would be a 5 because there are 5 zeros. And so again, those are pretty clearly combinational logic because in every case, for every one of my inputs, there is a single, unchanging, unambiguous output. And that defines combinational logic. But I can come up with a problem that kind of complicates things a little bit. So let's imagine I'm trying to design a circuit that's going to be used as a combination lock. So it's going to have 4 inputs, A, B, C, D. These are buttons on a little keypad. And the output of this digital logic circuit should be true. It should be basically tell my lock to unlock only if the correct sequence has been pressed, which we'll say in this case is a little star pattern, right? A, D, B, C, okay? Now, there's a little problem here, right? Imagine trying to define what this circuit should do if the C button is pressed. What should happen? Should it unlock or should it not? And kind of the real answer is, well, we don't know, right? There are some cases where pressing the C button should unlock the door or the keypad, right? If I've just prior to this pressed A, D, B, pressing the C should unlock it. But under sort of any other circumstance, pressing the C shouldn't unlock anything, which means, this thing, at least it's not really combinational logic, at least not purely combinational logic, because if I have my input here, which is C, there's not a single unambiguous output that sort of corresponds to that. Okay, so we need to sort of amplify our understanding of digital logic to be able to describe this thing. We will show you over the next couple of lessons how we're able to take a problem description like this and ultimately build a digital logic circuit that implements it. But to start with, let's just kind of ask ourselves the question: how do we describe this system? Because if we can start with a model, at least we can kind of work with that and rearrange it and maybe sort of incrementally get ourselves to a full implementation. Okay, so what we know is that this circuit here, it has our 4 inputs, A, B, C, D, from the buttons on the keypad, and it's got this 1-bit signal unlocked, which should go true when the correct sequence has been pressed. And so what I can say is, well, I know that this system has at least 2 sort of modes or states, right? There's a locked kind of state and an unlocked state. Or another way of saying the unlocked state is this is the sort of the system's in this state when it has detected the input sequence of A, D, B, C, right? That was the input combination, right? So then I might ask myself, okay, well, how do I get from my locked state to my unlocked state? Well, if my unlocked state is also known as ADBC, it detected the ADBC, I only get there if the person operating this device presses C from a state previously where the ADB were detected. So I'm going to depict that here, right? I've got over here on the right in my orange is my unlocked state. This is where, the output of my circuit is true. And I only get there if the C is pressed from the device being in the ADB detected state. Okay, so these circles here kind of are starting to describe the various modes or states that my system can be in. And I'm going to use these arrows to show transitions from one state to the next. And next to the arrow shows the specific input combination that sort of gets me from that state to the next. So that if I'm in this state here and my next input is a C, then I should go to the unlocked state because my user has typed in the correct passcode. And so, of course, let's work our way backwards, right? I only get to the ADB state if the B button was pressed from the AD detected state. I only get to the AD detected state if the D was pressed from the A detected state. I only get to the A detected state if A was pressed from basically anywhere. We'll call this sort of like none. It's sort of like a default state, right? So these 5 circles now are starting to describe what I want this circuit to, what I want my digital logic circuit to do. I'm sort of going to default into this none state, and as long as the person operating my device presses A, I'll move to this state. If they press D next, I'll go to this state. If they press B next, I'll go to this state. And then lastly, if they press C, they'll go to the unlock state. Okay, and this is the start of something called a state diagram. All right, a state diagram primarily has 2 things. Number 1, it shows all the different states or modes that my circuit can be in. We started by identifying the fact that this device, my combination lock, had 2 states, but based on the sequence of buttons we were trying to detect, we sort of expanded that out now into 5 states. And at least in this class, the states or the modes determine my output. So we'll only really look at finite state machines where in every state the outputs take on a known value. So clearly for these first 4 circles, right, my output, my unlocked signal is a 0, and then my last one, my output is a true, is a 1. So the state diagram shows, number 1, states and modes, which determine my outputs, and number 2, the transitions that occur between these states based on which inputs are present on my circuit. And so you can see here kind of the happy path, right, of selecting the correct values that take me from kind of a default state to the unlocked state. To round out my state diagram, though, to make it kind of complete, I got to add a couple of things. All right. So number 1, which you might have anticipated, right, is I got to list all of my input combinations. So some of you, when I said, hey, we're going to go to the unlocked state when the user presses C here, might have asked yourself, okay, well, what happens if they don't press C? And so that's something we need to add to our state diagram. So in this case, if A, D, B have been pressed and the user presses C, they go to unlocked. If they don't, they have to go somewhere else. And we have to, as designers of this system, determine where they should go. What I've decided is that if they press ADBA, that last A is potentially the start of a new correct sequence, right? The input could be ADB, ADBC. So I'm going to say, okay, if in this state the user presses an A, we're going to go back not to sort of the zero default no detected state, but to the A detected state. And if they press anything else, if they press a D or a B, then they should just go back to 0. ADBD is not the start of any correct sequence. But I need to be, very clear that I don't leave out any possibilities. So I've got a C here, an A here. If the result is not either one of those, so it's not A and it's not C, then I go back to this none state. So I need to be careful that, for all of my possible input combinations, I have them labeled where we should go in each part of the state diagram. Number 2, let's see what I want to, so you can see here kind of the last 3 things. These are all fairly simple. Number 1 is I need to make sure I've got my reset vector. So this just says that when power is first applied to my device, which state should it find itself in? For this one, clearly it's the no detected state, right? My default state. For all of my future state diagrams, I just need to make sure that that's annotated somewhere to be complete. Number 2, I mentioned it above, and it should come as no surprise that within each state, I need to define the output signal. So I'm going to use U here to talk about my unlocked signal. And what I'm doing within each little bubble, each state, is to say that, for the first 4, the unlocked signal is a 0, and it's only in this last one that the unlocked becomes true or high. And then lastly, occasionally I will take a state transition regardless of what else is going on with my inputs, And that might be the case here if, let's say, the device is unlocked. The very next thing that I'm going to say should happen is that, it should go back to the none state, the default state. We're going to assume sort of, that it unlocked, the user opened the door and got what they needed and sort of closed the door, so it should sort of go back to being locked and resetting itself. So regardless of what the input combinations, I'm going to say when I'm in this final unlock state, I'm going to go back to my default state. So I add that transition here, and then I can mark the fact that I'm going to always take this transition regardless of my inputs with a 1. That's sort of like the always transition, right? Because a 1 is always true. And so now, at least in this diagram, I don't quite have a circuit yet, but I can I can accurately describe what I want this system to do. Originally sort of described up here in my text. I've got a system of diagramming this, which allows me to describe what I want my logic to do. And we'll look in future lessons how we actually build that. For now, what I want you to sort of realize is that there are some problems that we can define with combinational logic, like we started with, that have a single unambiguous mapping between some input and some output. And if I ever find myself running into a problem where I don't exactly have that mapping, then I might need a finite state machine to solve that problem. And in a finite state machine, it's called finite states because there are a finite number of these circles that define my circuit. So what I can do is describe, start with kind of a conceptual understanding of what are the different modes in my system, what sort of states that device needs to be in, and then start adding transitions based on my input combinations. I'll make sure that I list all input combinations coming out of each state so that I know exactly where I'm transitioning if I, based on whatever input combination I have. And I'll make sure to add the reset vector, and within each state I'll add my output values. And this will allow me to describe my finite state machines. All right, that's all I got, folks. I'll see you next time.